It's a pleasure to be here. I'd like to thank the organizers for inviting me, particularly since I'm not known for sort of being kind of very close to the computational learning theory community, although I had personal connections to it. And a lot of the stuff I'm going to talk about today is things where learning theory is kind of difficult to apply to, and I'd like to sort of present this as a challenge for this community to study it. So I'm going to talk mostly about learning representations, or deep learning, as it's come to be known. You can think of deep learning as one particular way of learning representations. So we know that in the history of pattern recognition and machine learning, we've been doing a pretty good job at coming up with algorithms to learn classifiers and predictors of various kinds, always assuming that either the feature set or the kernel was given to us beforehand. And the kind of questions I've been interested in for a very long time before, from the first day I started working on machine learning, which was in the early 80s, was learning representations, because I thought from the start that it was kind of the secret towards sort of more powerful learning machines. And so that's why I sort of never had a huge interest for things like kernel methods and stuff like that, because they just were not solving the problems I was interested in. It doesn't mean that I don't think they're useful, but I think my interest is just elsewhere. So here is where my interest is. It's learning representations. And learning representations, I think, is probably the next step for AI, machine learning, as well as for things like neuroscience and cognitive science. Neuroscientists have no idea how the brain learns representations, and I think machine learning can help them with that. So how do we learn representations of the world, say the visual perceptual world, and by merely looking at the world, maybe acting on it as well? Neuroscientists ask themselves a similar question: how does the visual cortex organize itself to perceive, to turn itself into a visual cortex? The sort of connected question for machine learning would be: how do we learn feature hierarchies? The reason for hierarchy is going to become clear in just a couple of minutes. So the deep learning problem really is one of learning representations of the world by just looking at data. So traditionally, as we all know, pattern recognition systems have been built by either building handcrafted feature extractors followed by more or less generic classifiers, although the more modern approach to things like object recognition or speech recognition actually has another stage in it, in the middle here. The low-level features are fixed. In the case of speech, there are things like MFCCs. In the case of vision, there are things like SIFT and HOG. And the second level actually uses learning. Usually it's based on some sort of unsupervised learning, very simple one like k-means or sparse coding, to sort of turn the low-level representations into sort of mid-level representations, you could call it this way. And then it's followed by some sort of pooling and then a classifier, a supervised classifier. So, one more stage: fixed, unsupervised learning, supervised training. That's kind of the mainstream approach to speech and image recognition until very recently. But really, that model hasn't changed much since the early days of pattern recognition. When you look at the perceptron, that's pretty much what it is. A feature extraction followed by some sort of classifier. And maybe it's time after 50 or 55 years or so to move away from that model. If we look at how the brain performs vision, and I'm not a huge advocate for getting inspired by biology, but it's sometimes useful to get intuition from it. It's much more hierarchical. You have kind of for the sort of fast recognition process that people perform and animals as well, there's sort of a feed-forward path that we can trace, called the ventral pathway in the cortex, visual cortex, that goes into several stages, each of which has very highly nonlinear operations built in, and it goes through various areas of the brain called V1, V2, V4, IT, each of which has kind of several layers of processing, if you want. So you might have the signal might have to go through maybe 10 synapses or something like this, or 10 neurons, if you want, to go to the area of the brain where object categories are encoded. So it's not just, it's not shallow in the usual sense. It doesn't look very much like the kind of architecture that we've used so far. Okay, so it's sometimes useful to get a little bit of inspiration from biology, but it's also very dangerous because we don't know what's important when we look at a piece of brain. We don't know what matters in it. And so here is an example of what not to do. There's this guy called Clément Ader from the 19th century who built airplanes modeled after bats. And he didn't know much about aerodynamics. He was very good at building steam engines, but powerful and light steam engines, but not very good at stability and things like this. And so he built this airplane full size. The thing actually took off, flew 50 meters at 1 meter altitude, was completely uncontrollable, which is why you probably never heard of him. Every Frenchman, of course, knows about him, but but not on this side of the pond. This side of the pond is the Wright brothers. This was 13 years before the Wright brothers. So he was too close to the biology. He really didn't know what was important about it, and he hadn't figured out completely, the law of aerodynamics and stability. And we might ask the question, in our case, there are people in the world who got lots of money from various governments who claim that they can reproduce the functions of the human brain by basically simulating a giant brain on a computer. And I think it's completely nuts. I think it's just never, it can't possibly work if we don't understand what the underlying principles are. So what are the underlying principles for intelligence? What is the equivalent aerodynamics for intelligence, right? That's what we might want to go after in terms of sort of conceptual goals. Okay, so the architecture we might want to go after is something of this type where, we feed a raw input and we have it go through a whole bunch of transformations, each of which is kind of a trainable machine, if you will. And as a side effect of this whole system training itself to perform the task, it will kind of derive internal representations of the problem. So the first, if you're a theorist, at least some theorists I know, first question you might ask is, why do we need that many layers? Why can't we just do this with just 2 layers, like say this? Okay, have a kernel function, compare your input with all your training samples or a subset of them, compute a linear combination of this, and you're done. Now, so of course, someone has to give you this kernel function, which is just as complicated as coming up with a feature vector. But if you limit the complexity of this function here, it's pretty clear that there is a whole bunch of functions here that will require a very, very large number of terms in this sum to be able to do anything useful. Or if the number of terms is small, that means your kernel function here does all the work, and where is it coming from? So there's kind of a bit of a conundrum here, and you would think that some functions that perceptual systems have to compute are inherently sequential. They require to have a certain number of sequential operations for them to be computable with sort of a relatively small amount of resources. There's a lot of complexity theorists in the room, and people who have studied circuit complexity, I'm sure, who know that if you allow yourself to have a few layers of computations, you can gain an exponential factor on the kind of amount of hardware you need to compute a particular function. For example, let's take the example of n-bit parity. We know that we can do this with log n stages, or log n over 2 stages with XOR gates. But if we force ourselves to do it in 2 layers using the conjunctive normal form, we might need an exponential number of minterms. So it's just a very simple question of exchange of complexity between space and time, essentially, that we deal with all the time when we write programs. If we allow ourselves multiple stages, then we might gain a huge factor on the overall amount of resources we need. So it's very intuitive. I don't have any theorems to tell you to show you. You guys are the people to actually prove those theorems. But the basic idea is basic intuition of why we need multiple layers is just that. It's circuit complexity, basically. Okay, so there's a bit of a theoretician nightmare here, which is that when we start having multiple layers in a system, like say a deep neural net, and we try to train it using, say, supervised learning, we have loss functions that end up being non-convex. And if you have non-convex loss functions and you rely on things that, like minimal, empirical risk minimization and stuff like that, all those things go out the window because you can't prove anything about the optimality of your model. Okay, but if they work, it's actually worth maybe spending the effort trying to figure out why they work. So, so all bets are off with non-convex losses, but then again, every speech system ever deployed has used non-convex optimization. And it's not because they're non-convex that they don't work. Arguably, to some of us, the only interesting learning actually is non-convex. Because if you have a convex optimization to solve for learning, then the order in which you learn things doesn't matter. We know that humans, the order in which you learn things in humans matters. It's called pedagogy, right? I can start my talk with the last slide and then go backwards, but I don't think you'll get in the same state at the end if I do this. So even though the aggregated statistics is the same. So, there's the order in which you see things actually matters, and in which you learn things actually matters. And that suggests the fact that whatever loss function, the human brain is minimizing, if it actually minimizes a loss function, which is another question, it has to be non-convex. Otherwise, the order in which we learn things wouldn't matter. Okay, that doesn't mean that we can't actually, do AI without convex optimization, but it's sort of an interesting observation, perhaps. Okay, the other theoretician nightmare is that, if we have all those things with deep learning algorithms, we don't have any good generalization bounds. Well, actually, it's not true. You take a big neural net, it actually has a bound, a VC bound type thing, because its VC dimension is finite, but no tight bounds. Now, that could be a problem, except that I don't actually know anybody in practice who uses bounds to do model selection. I hate to say this in front of this crowd, but that's true. Does anyone know anyone who actually uses bounds in practice to do model selection, as opposed to, say, cross-validation? Raise your hands.
We also don't use it.
Okay, here you go. No hands. Okay, Leon, but I know it's not true. Okay. So you see, some of my best friends use bounds. So, it's hard to prove anything about deep learning systems, but then again, if we only study models for which we can prove things, we wouldn't have speech, handwriting, and object recognition systems today. Okay. On the other hand, it's kind of a smorgasbord of stuff for theoreticians, because there is so many things we don't know about all the methods that are used in deep learning, and I'll talk about them, some of them as I go, during the talk. So, deep learning is about representing high-dimensional data, or representing data in high-dimensional spaces, and there has to be interesting theoretical questions about this. What's the geometry of natural signals? Is there an equivalent of statistical learning theory for unsupervised learning, or computational learning theory for that matter? I mean, I know there are efforts along those directions in this community. What are good criteria on which to base unsupervised learning? Things like that. Questions that have been answered by this community for supervised learning, which I think, would be worth thinking about for feature learning, which is sometimes unsupervised. Okay. So let me talk about the state of affairs for deep learning today. It's been one of the hottest topics in speech recognition for about the last 2 years. The latest generation of commercial systems that do speech recognition are all based on deep learning. The ones from IBM, Google, Microsoft are all based on deep learning. The ones in the iPhone, which is actually indirectly produced by IBM through Nuance, they all use deep neural nets. And it's been a very, very fast transition from Gaussian mixture models to deep neural nets for acoustic modeling in the last 2 years. It's becoming the hottest topic in computer vision, mostly because of the last ImageNet competition. I'll come back to that. And it's becoming a bit of an interesting topic for natural language processing, although it's not there yet. And there's a huge interest from the applied math community into things like representing data in high-dimensional spaces. People who used to do harmonic analysis who now do sparse coding and stuff like that. Okay, so here's another piece of history which kind of indicates in what direction things are going. If you look at the history of handwriting recognition, speech recognition, now computer vision, object recognition, every time there's been an increase in the number of training samples that were available, people started using learning more and more of the system. So instead of just learning the classifier, they would learn, the mid-level features and now the low-level features in an integrated fashion. And every time a step like this that was previously built by hand has been replaced by a learning algorithm, essentially, performance has improved. So we just saw this in speech recognition. It's just happening also in computer vision. And it's been happening, it was happening before that. It happened before that in handwriting recognition back in the 90s. So there's sort of a very clear sense of history. As our data sets increase in size, as our machines become more powerful, we use learning more and more, and things become better as we replace more and more handcrafted modules in our system. It's a very clear path. So that's kind of a interesting thing to say for people interested in learning. If you rely more on learning and less on human engineering, things work better if you have more data. Nothing revolutionary there, but you have to kind of realize that that's going on. Okay, so I'm going to talk about convolutional net because everybody assumed that I'm going to talk about that, and also because they've become very popular in recent years for practical applications, and a number of companies have deployed image recognition applications, some of them speech recognition applications based on convolutional nets in the last year or so, last few months, in fact. So convolutional nets are inspired by biology to some extent, a little bit by the architecture, what we know about the architecture of the visual cortex. It has its root in the cognitron model by Fukushima in the 70s, which itself had its root in the work of Hubel and Wiesel, classic work in neuroscience from the 60s, where basically the first couple stages of the visual system, the visual cortex, are seen as filter banks. Okay, so you have an input here or a bunch of planes of input, which might represent, say, color planes, for example. And then you have a bunch of planes here that extract features from the input using a convolution kernel, essentially. So you take a convolution kernel, swipe it over the image, you get, so it's like a linear filtering, you get the result of the application of this convolution to the input. And for different filters, you'll get different outputs. Each of those is called a feature map. You pass that through some nonlinearity. The latest, most popular nonlinearity is called ReLU, rectified linear unit. So it's basically a half rectification, positive part, very simple nonlinearity. And then there is a second operation called pooling, which kind of aggregates the answers of the filters over a small region, sometimes over multiple features, and the resolution is reduced. That is to build a little bit of shift invariance and distortion invariance into the system. So this is sort of, pretty old idea. The modern versions use what we call multiple stages, each of which has 4 layers or so. One that performs some sort of contrast normalization, followed by this filter bank I was just telling you about, the nonlinear operation, this rectified linear units I was telling you about, and then this feature pooling. And then you take this module, you stack multiple instances of it, stick your favorite classifier on top. Usually the whole thing is trained with back propagation, just gradient descent, basically, so a stochastic gradient descent, and you use backprop to compute the gradient of whatever loss function you want to minimize with respect to all the coefficients in all the filters in every layer. The pooling operation is just any kind of symmetric operation, a max, an average, square root of some square or something of that type. Let me give you show you an old animation of a convolutional net that was trained to recognize handwritten characters. The reason I'm showing this to you is because I'd like to point a property of feature extractors that I think is important. So this was trained entirely supervised to classify essentially MNIST digits, you can think of it this way, with a little bit of invariance to position. Now, look at this particular pixel here. As the number 3 here goes up and down, it goes from white to black to white. I have a hard time keeping it fixed, but okay. So what that means is that the line formed by all the translated versions of this 3 is not flat. It's got a curvature because one of the coordinate goes from one value to another value back to the first value. So it's got to have some curvature to it. Now the bad news is that, so if you imagine the set of all deformed threes, it's a surface whose intrinsic dimension is the number of possible deformations you can do locally. The similar manifold for digit 8 is sort of entangled with the 3. It's very highly nonlinear as well, but it's not linearly separable from the one of the threes. Most of the pixels are common, but the curvature of the two manifolds is very high. So you can't just do linear separation between them. You have to extract features. We know that. Okay, so look at if you look at any value that appears here on the top layer, there's hardly any that goes from white to black to white or vice versa. They go from less gray to more gray or vice versa, whatever that means. And what that means is that the manifold of stuff of deformed translated patterns here is flatter because of all the process that went during training of this. Of course, it happened to be this way because the layer that came after this was a linear classifier, and linear classifiers like to have linear subspace to separate from. So that's precisely why it happened. But it's a good property to have for a set of features that the manifold of variations you don't care about is flat. Perhaps there is some idea on how to derive a proper criterion for unsupervised training based on this sort of flattening manifold kind of idea. Let me skip this in the interest of time. Okay, so there's a whole number of tasks for which we know that deep convolutional nets are the best method so far, for which we have the record. Handwriting recognition goes back a long time. OCR in natural images, traffic sign recognition, pedestrian detection, volumetric brain image segmentation, human action recognition, object recognition, scene parsing from depth images, speech recognition, breast cancer, cell mitosis detection. This was actually a Kaggle competition that was won very recently. All of those were won by purely supervised convolutional nets. Okay, so things like, traffic sign recognition, street number, is another application that we built on EEG analysis. This is one from Sebastian Song's group at MIT. This is student Viren Jain for segmenting brain tissue, where he applies a convolutional net to a small volume of voxels and trains it to classify the central voxel as being the boundary between two cells or not. This is a piece of brain tissue, and after the network has produced labels for each of the things, it can sort of reconstruct the brain circuit. Here is only showing a few percent of the neurons. They are very densely packed. So it's a very interesting application to connectomics. But here is really what caused the big commotion in the last few months. Back in October, or a little earlier than this, Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton won the ImageNet 2012 competition. So this is one of the main competitions in computer vision for object recognition. And they won it by a huge margin. They got something like 15% error rate by some measure, where all other methods that competed in the same competition got around 25-26% error. So it's really a big jump. It's not just a small improvement, it's a big jump. And it's essentially a big convolutional net using, as Shai was saying, all the tricks I came up with in the last 20 years, plus this dropout technique. But really what made this, the secret of what made this successful is a very efficient implementation of this on GPUs, which allowed them to train on a very large data set of 1.3 million training samples in about a week on a single GPU, or actually on two GPUs. The filters that are learned at the first layer are somewhat interesting. The color and the black and white ones are separated for, it's kind of an artifact of the way that the system was designed. It works really well. Here is another example. This was kind of a similar system that was developed at NYU, not by me, by Rob Fergus and his student Matt Zieler. And so they have a convolutional net that's somewhat similar to Alex Krzyzewski's, but a little different. Also trained on ImageNet, also using ReLUs, using contrast normalization at the layer, These are the filters of the first layer that are trained. It also uses this dropout regularization, which is essentially a sort of very brutal regularization that consists in killing half of the units in the top layers and hoping that the network will recover from it. And it's a different half that you kill at every sample. I mean, you would think it's, murderous, but it seems to actually help a little bit. It uses SGD, not a particularly sophisticated form of SGD. There is an online demo of this that you can play with, ratio.cs.NYU.edu. You can upload images and it will kind of tag it with all the categories it finds. It works, just as well as Alex Kuzhevsky's, a little better maybe, but I'm sure Alex has better versions now, but he's not going to talk about it. Now that he's at Google. And but here is an interesting point about this network. The features that it learns are fairly generic. So if you take the network that it trained on ImageNet, chop off the last layer, and then just retrain the last layer on a different data set, say Caltech 256, you basically get state-of-the-art performance with only 6 training samples per category. I think that's amazing. So Caltech 256 is not a particularly interesting set now. It's kind of out of date. But the state-of-the-art is here. Previous state-of-the-art is here. You get to the state-of-the-art with 6 training samples per category, just using the features at the output of this convolutional net. I mean, right before the output layer. Just retraining the classification layer. What that means is that the features it's learned are really generic. You can use them for just about any object recognition task that you could imagine. Here's another example. This is with the Pascal VOC challenge. So here, it's not as dramatic, but the accuracy is pretty much state-of-the-art, a little below, mostly because of the nature of the labeling of the Pascal VOC dataset. But it's kind of impressive because only the last linear classifier basically is trained here on this dataset. The features just come from ImageNet. Here's another example that was done in my lab by Clément Farabey and Camille Coupry. This is for labeling images. This is called the semantic labeling problem or scene parsing, or there's various names for it. And the problem here is to label every pixel in an image with the category of the object that it belongs to. Okay, so sky, grass, and trees, and blah, blah, blah. And so it's a little more complicated than object recognition because you kind of have to figure out what every pixel belongs to. And we just used a convolutional net, but a multi-scale kind of convolutional net, where you take the input, you build a pyramid out of it, where you have kind of lower resolution versions of this image, and then you apply the same convolutional net. So let's say you want to classify the central voxel here, the central pixel here. You apply a convolutional net whose window, sort of context window, that is going to influence a particular output is, say, 46 by 46 pixel. If you apply the same convolutional net to this image, it will also get influenced by a 46 by 46 window, but now since the image resolution is half, it's going to take into account a context that's twice as big, same here. So this guy is basically going to see the entire image at quarter resolution. And you combine the features that are produced by the 3 copies of this convolutional net with they all have the same filters, concatenate them, feed them to a classifier, you train this whole thing supervised on a couple thousand labeled images that have been labeled at the pixel level. And every decision for a particular pixel is going to be taking into account this 46 by 46 window, and this 46 by 46 window, which really is 92 by 92 here, and this 46 by 46 window, which is really 184 by 184 here. So it can use this huge context to make a decision. And this pretty much works as state-of-the-art. So the best result on this data set on the pixel per pixel accuracy basis is 82%. Our system gets 81.4 instead of 81.9. We also have a simpler system that is slightly lower by 1%, but is about 100 times faster because it doesn't use any kind of complex graphical model as post-processing. It uses a very, very simple post-processing after the convolutional net. This is on the Stanford background dataset that has 8 categories. This is the CFlow dataset. Oh, I should have mentioned there are 2 measures of performance. This is pixel accuracy, and this is pixel accuracy where an error counts for more if it concerns a category that's rare, so that you pay more for missing a human, even if it's only a few pixels in a large image. So it's it's a more accurate measure. On this one, we actually beat everyone. This is on a CFlow data set with 33 categories. Then again, we pretty much have the record here. Depending on how we train it, we can beat the record either on pixel accuracy or on class normalized pixel accuracy. And this is a data set with 170 categories where nobody does well. We do just less badly than, Lana Zednik. This is Lana Zednik's group at University of Illinois, Urbana-Champaign. So here are some examples of results. This works really, really well. This is the 33 categories, got trees and buildings and windows and roads and everything, sky, sand. And you'll see an example of a video here. So each frame here is processed independently, which means there's no sort of temporal consistency here. And it makes some stupid mistakes, like when the ground is bright, it's classified as sand. This is actually Greenwich Village, so I can tell you there's no sand. There's no beach. So this is someone riding a bike with a panoramic camera. The pictures have been stitched together. But it gets most of the important objects like humans, people, and trees and stuff like that. Modular lighting problems.
How much speed did the FPGA give you over CPU?
So a CPU, on a sort of beefy Mac laptop, this runs at about 2 frames per second. The GPA, if we run entirely on the FPGA, it would run at about 20 frames per second, except that the communication with the FPGA board is actually slow, so the system time is actually slower. Here's another example. This uses temporal consistency. It's kind of a similar video, has fewer categories, but it's the same video. And there's a lot less kind of jumping around of categories here because of this consistency over time. It's just a post-processing. There's no change to the convolutional net. You can apply this also to images that have depth information with them, so collected with the Kinect indoor data. And again, this has the best results that we know of. And this is without temporal consistency and with temporal consistency. Okay, so enough for supervised stuff. Let's talk about unsupervised learning. So how do we devise unsupervised learning algorithms that will allow us to pre-train the layers of, say, a convolutional net or any kind of deep learning system, hierarchical feature extractor, using unlabeled data? Because, of course, we have a lot more unlabeled data than we have labeled data. Now, it used to be that all of what deep learning was about was this. And there was kind of a minor side interest in things like convolutional nets, which seem to work just fine if you just train them supervised, as long as you have enough data. And because of the because of the fact that we now have large data sets, large labeled data sets, there's sort of slightly less interest in this kind of unsupervised learning things because the supervised stuff works so well. So even people like Jeff Hinton, who kind of were really, really interested in this unsupervised learning stuff, essentially for practical purpose, is just doing supervised convolutional nets now. He actually calls them dread nets, which stands for deep rectified networks with dropout. D-R-E-D, right. Okay, so how do we do unsupervised learning? So, there's this hypothesis that the manifold of natural data, if you take patches from natural images, the set of possible patches you will observe is actually a low-dimensional subspace of all possible combinations of pixels you could come up with, right? So there is this, picture of sort of the manifold assumption. And some people don't agree with this. People like Stéphane Malin say that's kind of a wrong picture to think about. I think I agree with him, but it's still useful. So what we'd like to do is, ideally, what an ideal feature extractor should do is take a bunch of samples, data points, and tell you if there is a manifold of data, tell you where you are in the manifold with a number of components, and then have a separate set of components that tell you the distance to the manifold in all the other dimensions in the ambient space. Okay? So what you really want is you want to kind of factor two sets of variables. One is where you are in the manifold, and the other one is where you are away from the manifold. Okay, so if you had, for example, the set of manifold of possible faces, all human faces, it's a high-dimensional manifold. For a particular person, it's bounded by the number of muscles in your face and the number of degrees of freedom that you can move around, which is 6. And then if you include everybody, then there is some sort of number of dimensions, basically bounded by the genome of how many different faces you can have, modulo accidents. And so if we had this manifold, then if we had this kind of feature separation, you could use the first part to tell who you're looking at and what expression they're making, and you could use the second half, the part that tells you, how far away you are from the manifold, to tell you if it's a face or not, or if it's something else. So, disentangling the explanatory factors of variation is really what unsupervised learning should be about. There is a general idea, which is sort of emerging a little bit. There is no kind of concrete or theoretical justification for it, but it's just what people end up doing in the end, which is that a feature extractor should really be composed of 2 steps. A nonlinear step that basically embeds the input into a very high-dimensional space, or a high-dimensional space. Okay, this is similar to the kind of kernel kind of thing, right? You embed things into a high-dimensional space so that things are more easily separable in that space. Same stuff, except, not based on the kernel trick, based on other things. It has to be nonlinear, because if it's linear, it doesn't do anything useful for you. It's like a no-op. Okay, so embed your input into a high-dimensional space in some sort of nonlinear way. But then what you do here is that you're breaking the space apart. There are things that are semantically similar or even identical that will end up in different bins in this representation, maybe very far apart. So the second step, which is sort of a generalized pooling, similar to the pooling we do in convolutional nets, is to regroup the things here that are supposed to be similar. Okay, so whenever you get 2 vectors here that represent 2 faces and they happen to be very different, you somehow encode them in such a way that here they end up being similar.
And that's linear?
It may or may not be linear. I'm sorry, I didn't pick up. Oh, you were, okay. Probably not.
Probably.
No. What people do in practice is something like L2. So square root of sum of squares of some components, subset of components.
So can it be sort of picking some landmarks and just representing every object as the vector of distances from those landmarks? Yeah, right. Okay, so here's an example very concrete example for the sort of mainstream approach to computer vision until convolutional nets, right? So the Lazadnik PRB mesh kernel SVM, for example. Okay, well, so for mid-level features, what you do here is k-means. So you take, say, a sieve vector, you run it through a k-means algorithm, and the k-means is going to give you a binary vector with all zeros and 1, 1 at the location of the prototype that's closest to the input. Okay, so it's just a winner-take-all kind of encoding, if you want, a word, right, a visual word. And the pooling here takes all of those feature vectors for the entire image and just average them, or combines them in some way. So now what you get is a histogram of words, and you can feed that to your favorite classifier. And the goal of this is to basically give you shift invariance. So once you do this aggregation, the position of a feature doesn't matter anymore. It's just the presence of it that matters. Okay, so you've regrouped things that were dissimilar. Now it turns out when you do something like sparse coding here, it works much better than if you do k-means, because sparse coding preserves a bit of a similarity between things, right? Which k-means just completely explodes. Okay, so we have this manifold picture. We have a bunch of data points, and what we'd like is to kind of learn a function that gives us the dependency between x1 and x2 here in this case. What we're going to do is we're going to, the sort of general framework I think that is the most appropriate for this is the sort of energy-based framework, which consists in essentially learning an energy function, or think of it as a contrast function that tells you if I give you a point, and the contrast function gives you a scalar that tells you whether you are on the manifold or not on the manifold. And if the function is able to do this, internally it has to be able to kind of do this disentangling of features, right? It has to be able to tell
in which direction the manifold is, what's the closest point on the manifold, and where am I going on the manifold, and things like this, right? So that's all we're going to do. We're going to train a system to produce a single scalar, and the scalar is going to be some sort of contrast function that tells you how far away we are from the manifold of data. So let's say we take samples coming from this spiral here, and we run PCA. PCA with only one dimension. So it's a two input problem, two output problem, and we do PCA with one principal component. PCA will find this main axis here of the point cloud, and the reconstruction error would be 0 for anything that's on the principal axis, and will grow quadratically as we move away from it. If you use sparse coding, it will sort of wrap up the set of points into a kind of union of planes, if you want, or union of lines, so that the sum of the distance to all the lines ends up being the function we're looking for. K-means will just put a whole bunch of prototypes all around the surface. This seems perfect, but it doesn't work in high dimension, of course. Okay, so let's concentrate on this idea of sparse coding. So sparse coding uses an energy function of this type, which has two arguments. One is the input, and the other one is a code vector, which is really a latent variable that we're going to infer. And the energy function is the square reconstruction error, where we multiply the code vector by some matrix called a dictionary matrix, and then we add a regularization term, which is the sum of the absolute values of the components of the code. If we know the dictionary matrix, given a y, we find a z here that minimizes this energy function, and that gives us our feature vector. It's going to be high dimensional and sparse. Okay. So it's a nonlinear mapping. The one that maps y to the optimal z is nonlinear mapping. But it's slow to compute because you have to do this argmin operation. We can learn the dictionary matrix, of course, with Olshausen and Field told us how to do this a very long time ago, using just SGD, basically, just stochastic gradient descent, to minimize the overall average energy of a collection of samples, training samples. The columns of W have to be normalized for this to work. And the manifold assumption that's hidden behind the sparse coding is basically that the data fits sort of a union of low-dimensional planes, where the dimension of each plane corresponds to the number of components in Z that are non-zero once we do this minimization. So in general, though, we have several ways of designing unsupervised running algorithms. One is, number one is to construct the energy function so that the volume of stuff that takes low energy is fixed, because the problem we have is that we have to build this energy function so that it has low energy on the points, on the data points, on the manifold, but higher energy everywhere else. And it's easy enough to tweak the parameters of an energy function to take low values on the points, okay? Just do a gradient descent. But then how do you make sure the energy is high everywhere else? And it's basically the partition function problem that people have been hitting in graphical models and stuff like that. It's very similar in spirit. So you want to construct, one strategy is construct the energy so that the volume of low energy stuff is fixed, so that if you give low energy to some points, the other points will automatically have higher energy. PCA is one of those, K-means is one of those. The second strategy is to push down on the energy of the samples and push up on the energy of everything else. This is a strategy used by contrastive divergence, which is used to train restricted Boltzmann machines. This is also a strategy used by maximum likelihood when you have a log partition function as a contrastive term that pushes up on the energy of other stuff, but it's very expensive to do if your partition function is not tractable, or doesn't have a tractable gradient. So you have to use Monte Carlo methods and stuff. And the third one is to use a regularizer to limit the volume of stuff that can take low energy. So basically build your model in such a way that it has a regularizer, and by minimizing this regularizer, it sort of shrink wraps the stuff of low energy into sort of in a small volume, if you want. And that's basically what sparse coding does. The sparsity term limits the volume of stuff that is allowed to take low energy. That's essentially what it does. Okay, so the sparse coding method is what we call a decoder-only method that has a simple function to compute that goes from the code to the input, which means you have to run an optimization algorithm to figure out the optimal code for a given input. So what we're going to do is we're going to add to this a sort of a feed-forward function that goes from the input to the code, and we'll attempt to predict what the optimal code is. And this function would necessarily have to be nonlinear. In the case of sparse coding, we call this PSD, which means predictive sparse decomposition. We could give various architectures for this. Let's say a simple neural net of some kind. And so here is the algorithm running, this PSD algorithm running on a set of natural image patches. And what I'm representing here are each square here is a column of the WE matrix represented as an image of the same size as the input. So you get, in the end of the training, you get sort of oriented Gabor detectors, which is what's more or less expected. Now, to design this encoder, this G function, former postdoc of mine, Carl Greger, has this really brilliant idea of essentially emulating an algorithm that we know will produce the optimal Z called FISTA or ISTA, iterative shrinkage and thresholding algorithm. And the ISTA algorithm basically is this kind of iteration where you take the input, you multiply it by an encoding matrix, and then you pass it through a shrinkage function, each component, multiply it by a square matrix, which is you can think of as a lateral inhibition matrix, add it to the previous result you had, and iterate this loop. So it's kind of this recurrence here. What we're going to do is we're going to learn, instead of using this definition for S and that definition for WE, we're just going to learn S and WE. And so you could think of this as a recurrent neural net of some kind with two matrices WE and S, and we're going to train this recurrent neural net, which has a bounded complexity, to do the best approximation it can of the optimal sparse code. And this works really well. In the interest of time, I'm going to skip the result. Just to say that we've applied this to kind of various things, including one where we have criteria that combine this reconstruction, the sparsity, as well as a sort of prediction. And this was a recent paper by Jason Rolfe and myself at the ICLE conference. And this produces very interesting results that we've never seen before in neural nets for recognition, in which inputs are kind of decomposed into sort of a prototype, if you want, plus a whole bunch of little modifiers of this prototype that turn the prototype into the observed input. I don't have time to go into the details, but I can tell you more about this later if you want, if you're interested. Another version of this uses convolution. So instead of using sparse coding as a linear, just a matrix, we view it as a bunch of convolutions applied to feature maps to reconstruct the input. And also use this PSD algorithm. And the result of this, for various reasons that I'm not going to explain too much, is that we get much more diverse filters, largely because the system is trained now at the image level and doesn't need to learn translated versions of all the filters. And so it ends up having more resources to spend on learning very diverse filters like center surround, crosses and corners and gratings of various kinds. So you get much more diverse filters doing this than you would get with standard patch-based sparse coding. That's another example here, as we increase number of filters. Okay, so how do we use this to pre-train a convolutional net? We take one of those PSD sparse autoencoder. This is really a sparse autoencoder in the convolutional form to pre-train the filters of a convolutional net. And so wrapped into this encoder, we have the input, the filter bank, and the nonlinearity, and the pooling really resides in the next stage. And once we're happy with it, we get rid of the decoder. We just run through the encoder, run our training set through this, and then stick a second stage of that, train this, unsupervised, then get rid of the feedback again, just keep the feed-forward path, stick a classifier on top, and now what we have is a full convolutional net that we can train supervised, but it's been pre-trained to essentially carry as much information as possible about the input all the way to the output, and so we start from a pretty good place. So it turns out this really helps in situations where the task you're trying to learn is very poor in terms of the diversity of labels that you have. But for a big data set like ImageNet, it doesn't seem to make much of a difference, perhaps in speed of learning. We're still exploring this, we don't know. But on things like pedestrian detection. So pedestrian detection is a case where you have lots of images, they're very diverse. The background category has a huge amount of variability in it, but you only have two labels. It's either a pedestrian or not. And if you train a convolutional net to do this, the features you get at the top layer are really bad because the label doesn't give you any information really about what's in the image. It only gives you one bit of information. So using this pre-training actually helps the feature be more kind of generic, if you want. And it actually makes a difference in performance. So this is a false negative versus false positive rate. So this is the false positive per image. This is one false positive per image right here. And this is the miss rate. And all of those curves are from all kinds of systems published in literature. This is a convolutional net that's been trained purely supervised, and this is the same one that's been pre-trained with this unsupervised training, and then refined supervised. So it makes quite a big difference. It goes from, middle of the pack to basically record holder for this data set. This is the INRIA data set. This is the kind of filters you get after training. And that's a video of the system in action. There's an important point I have to make, which is that it's very easy to turn a localized recognizer or detector that is a convolutional net into a full-fledged detector on a full image. It's very cheap to do this. It's a point that a lot of people miss, but it's really the case. Here's another example. This is in front of our lab. Here we kind of lowered the threshold so that we get some of the false positives to see what they look like. There are a few. So there are various forms of this for sort of invariant recognition, where we build the pooling inside of this regularizer for things like that, where we can organize the features into topographic map and do a group sparsity on groups that overlap each other. And the system organizes itself so that features that fire together end up being in the same groups. And so you get this sort of nice looking topographic maps, which basically are not particularly interesting for people like us in machine learning and computer vision, but they really kind of resonate with our friends in neuroscience. And they produce nice colored pictures, which I'm showing to you without explaining. Okay, I'm not going to go any further than that, and because I'm out of time. And I'd like to mention sort of a few issues I think that are of a somewhat theoretical nature that we really don't understand about deep learning. The first one is, what is the nature of the loss function that we're minimizing with deep learning? It's kind of a practical problem, practical optimization problem, if you will. Essentially, when you train a deep neural net, the cost function has lots and lots of saddle points. It's not just the local minima that are annoying, it's the saddle points. Because there's a big issue of breaking symmetries, deciding if one unit should do something and the other unit should do something complementary, or if it should be the other way around. So the symmetry breaking issues, which are the issues that limit the speed of training. Convolutional nets traditionally haven't been victim of this, which is why they've been one of the few very deep neural nets that have been in use for a long time. It's because they don't have that symmetry breaking problem to the same extent. They have it, but not to the same extent. So it's kind of one issue. Another set of issue is something we didn't understand 20 years ago, is that the systems that seem to work best are the ones that are ridiculously over-parameterized. We make the networks bigger and they just work better, even if we have limited amounts of data. And what we have to do is just regularize the hell out of them, using things like dropout and things of that type. But even if we don't regularize them, they work surprisingly well, and we don't understand why. The effective VC dimension of those things is much lower than what we think. Let's see. Then I think the biggest issue, I think, is how do we formalize unsupervised learning? What really is a good criterion for training an unsupervised system? It's always been a problem of mine to figure out, how do you even test if an unsupervised learning system works, right? What's the criterion? And the criterion is, train it to extract features and then train a classifier on the features and see if it works, right? At least that's an objective criterion. But it's not a good criterion to use for training unsupervised because you're not allowed to use the labels. So how do we design loss functions for unsupervised learning? How do we, and what are the principles on which it would be based? So this energy-based stuff is a little more general than the usual sort of maximum likelihood formulations, probabilistic formulations, but maybe it's not the right one. So, thank you very much.